Let us now discuss the expression for displacement current. We saw in Ampere Maxwell law is given by curl of B bar is equal to mu times J bar plus dou D bar by dou T. So here we got a new expression that is called as the dou D bar by dou T, and it is similar to this current density J bar. So this is therefore a kind of a new type of current, and we say that it is called as the displacement current density. So what is this displacement current then? So that is what we want to obtain the expression for the displacement current. So both J bar and dou D bar by dou T have the same dimension, and both of them produce the magnetic field there. Let us come back to the AC circuit involving a power supply, a oscillator with the voltage V given by V naught e power of I omega t, and it's involving a capacitor, and the distance between the plates of the capacitor, let us take, is D. The area of the capacitor is say A, and the displacement current which is passing between the plates of the capacitor, let us call it as ID. Here we can also remember the basic relations, that is the flux density vector D bar is equal to epsilon times the electric field vector E bar, where epsilon is permittivity of the medium, and also the electric field vector E bar can be written as V by D. Electric field magnitude, not the vector, the magnitude is equal to V by D. So displacement current now can be written as ID is equal to the density into the area. The current density, that is the displacement current density, is dou D by dou T multiplied by the area of the plate, that is A, we get the displacement current ID. Now replace here D by the relation epsilon E bar, and again E we will replace by the relation V by D. Therefore we get epsilon A into dou E by dou T by substituting for D here, and then we can substitute E by the second relation, the voltage applied by the separation between the plates D, and then we can get here epsilon A by D dou V by dou T. Now therefore the displacement current ID can be written as epsilon A by D dou V by dou T, and V is replaced by the voltage applied, the AC voltage applied, V naught e power of I omega t. So you get dou by dou T of V naught e power of I omega t, and differentiating this with respect to T partially, we get I omega into V naught e power of I omega t. So I omega taken outside, we get epsilon I omega A by D V naught e power of I omega t. Therefore we can write the displacement current expression as ID of T is equal to epsilon I omega A by D, and this is V naught e power of I omega t is nothing but the voltage applied, therefore we can write it as V of T. So this is the expression for the displacement current that is found in the case of the AC circuits, and because of this displacement current we had to make the changes in the Ampere's law, and the corrected equation we got called as the Ampere Maxwell law. Now what are the characteristics of this displacement current? It is not like the regular current. It appears in the time varying conditions like the AC circuits, and it does not involve any movement of charges, but still it can produce the magnetic effects. So this is the characteristics of this displacement current. So I obtained the expression for the displacement current like this.